intersect and then sort of tilt it to where you can see that part. If you want just this surface, then you can now enter each of those equations parametrically with those restrictions on u and v, or phi and theta. And then that'll give you just that particular shape. That's the cool thing about parametric surfaces, is the way it kind of allows you to be versatile with the way you're representing your surfaces. So let's see. This one, I'm going to have to use u's and v's here, so sorry about that. Sine u times cosine, cosine, no, I always miss that. What's it do? U times cosine v. There we go. And then 2 sine u times sine v. And then 2 cosine u. So I'm letting u play the role of phi. I'm letting v play the role of theta. So if u equals phi, I want u to go from 0 to pi over 4, which is about half of 1.57. So about 0.785. And then let v go from 0 to 2 pi, so all the way around. So I'll just stick back to the 6.28, 31853. So see, there it is. There is our yarmulke in space. That is the portion of a sphere. So if you kind of look at it crossways like that, at that lateral cross section, you can see the circular behavior of it. It's just that patch of the sphere. And then if you overlap it with the graph of that cone, that 45-degree cone going up like that, it cuts into the sphere with a circular intersection and gives you just that patch on top. And see, now that you got this equation set, you can do any part of the sphere you want to. If you want the lower half, that's only going to be a function of phi, so essentially that's a function of u here. You let phi start at 0.785, and then let it stop at pi, so about 3.14-ish. Okay, 159.27. And so that gives us, hey, what's the deal? What's the deal? Oh, it defaulted this back to 0. Sorry about that. Okay, so here is the previous yarmulke patch removed, and now it's everything from pi over 4 all the way down to pi for your phi values. Okay, makes a lovely little vase or something to put watering plants in. Maybe a fishbowl.
Yeah, fish looks like an eyeball.
Well, this thing I hear makes me think of what's his name, the fast food guy.
Jack in the Box.
Yeah, Jack in the Box. He just needs a little cap to finish his Jack in the Box face. Okay. So where are we going with all this parametric surface business? Okay, we're leading to surface integrals, but see, that's going to be Thursday. So that at best is going to be the bonus topic on your test 4. But one thing that will actually finish test 4's material proper is at least calculating surface area. Okay. I'm going to narrow it to where you're only calculating surface area for parametric surfaces. So, in light of that, going to our ABC homework packet that's really hard to decode, but if you go to this section on parametric surfaces, you can kind of get a rough idea of what I mean by matching. The way a matching problem could pop up for a parametric surface would be something like this. See, the first few problems on the homework here, I give you the vector equations for 5 surfaces, and luckily it's a 1-to-1 correspondence. So there's no red herrings thrown in here with this matching problem. Each of these equations here represent a unique graph down here. And I tried to, probably looking at these pictures online, you can see them a little bit better than what you can see here. But one's a plane, one is a cone opening on the y-axis. This one is part of, and fortunately it's on paper so we can't rotate it, but this is part of a hyperbolic paraboloid, aka saddle or aka Pringle. But it's only in the first, where x and y are positive, so that might help you kind of narrow it down. A paraboloid opening along the positive y-axis, and then part of an elliptic cylinder that's for positive x's and positive z, but for negative and positive y's. So in each of these equations, some of the equations are independent of u and v, but some of the equations actually give you restrictions on your u and your v that'll help you narrow it down to what the choices are. So if u and v are independent, in other words, if there are no inequalities that tell you the restrictions on u and v, like in A or D or E, just assume, just look at the pairings and think about what kind of shape u sine v here and u cosine v there would put in the xz plane. And then if your y component is u squared versus u, that could give you, well, maybe one of those two surfaces.
Would that be 5 for D, 5 for D?
With D?
Gosh, I'm sorry.
So Roman numeral 5 there would pair with which one?
Man, I don't know. I'm just
No, you're
kind of
right.
here.
What's the major difference?
Because that's what I thought
So
was
y
the
direction is
paraboloid.
squared here versus
so
linear.
you're going to make it a paraboloid.
If the y direction is squared, it should give you a
Paraboloid.
paraboloid. If the y direction is
Like
linear,
is 3.
well, not a straight line,
Cone.
but it won't have the paraboloid cross section. It'll have a linear cross section
That's a 45-degree line.
1,
indicative of a cone.
B is 4,
Yeah.
and that makes A 2.
Okay, well, so we've done it. A is independent of u and v, and A, linear use of u and v all the way across the board. If everything's linear, what kind of shape should it make in space?
Linears.
Well, linear in 3D. In
Plane.
2D, it's a line. In 3D,
Plane.
it's a plane. Yeah. So it should be entirely
I didn't even
flat.
look through 2. That's
Well, I
just
mean,
kinda
it's tilted,
defaulted.
but it's, I hate to
Okay.
put something on it, but it's flat, it's a plane. Okay. So then you got to double check, B and C we've narrowed down to being Roman numeral 1 or Roman numeral 1.
Yeah, B is
5, 4
B is
there.
4, C is 1, A is
Okay.
2.
Yeah, the cosine sine
D
pairing
is
on B
D, or
helps you
4,
match
5,
it with
D
4.
is 3.
And then there's
No,
the
no, other way
equation,
around, D is-
z equals x squared minus y squared gives you the equation of a paraboloid, a hyperbolic paraboloid, a parabola. And then that's the lame version of the parameterization, just letting y equal u and x equal v, and z equals, well, in this case, y squared minus x squared. So it should give you that saddle. But with that restriction, if u and v are restricted from 0 to 1, that means x and y are restricted from 0 to 1. So it gives you just that patch right there. So boom, that's done. That's how you do matching. The other ones, you're prompted to actually find a parameterization for a surface. In this first one, you're parameterizing a plane inside of a cylinder. So how would I get every point that's inside of a cylinder of radius 3? Every point that begins at a radius of 0 and stops at a radius of 3 in the xy plane. What parameterization would that help me with?
Polarization.
Polar, yeah. Let x equal maybe u cosine v, let y equal u sine v. And then u needs to range from, since u is the polar r value, you let u go from 0 to 3, because that'll give you every continuous circle from the origin all the way up to a radius of 3. Let v, theta, go from 0 to 2 pi. And then how the heck would you get this? Don't think too hard about it. We've done 2/3 of it so far. So far, we've committed to letting x equal u cosine v, and let y equal u sine v. So to guarantee you're on this surface, your z equation should be, well, 5 minus...
Just 5 minus u cosine v minus u sine v.
That's it. You just substitute the xy equations in terms of u and v in here, and it'll guarantee to be points on this plane that are based on points inside that cylinder. You see? Okay. Portion of a sphere that's lying only on the positive y-axis side of the xz plane. So maybe review our example that used the spherical parameterization and think about how your thetas and your phis should spin up there. No more freebies. No more freebies. All right. But the only other thing I'm prompting you for is calculating surface area. So when you get to the surface area part of part C, I only want you to do it for a parametric surface. So there are some surface area problems. And again, this is still the same set. The first 3 right here, you're asked to determine the surface area of the following parametric surfaces. So I do want you to try 3, A, B, and C here. But you can actually stop right there. The remaining surfaces are well, you can parameterize them if you want to, so you can turn them into parametric surfaces. But there is another formula for surface area in terms of, z equaling a function of x and y. So you can completely dismiss the whole parameterization need by going back to old school surface area. But we focus so much on parametric surfaces, that's what I want your focus to be. So here on section, again, the section number is section C, stop at 3 ABC. So,
But that whole package is on the exam.
yeah, well, no, the exam material is going to stop with surface area.
Oh, so it's not.
So what I mean by stop here is, not just for this section, that technically stops the material for test 4.
Okay.
So I'm not going to put a surface area problem that involves these. So I mean, you can look at the solutions and see how they're done, because I've got the solutions on there for this. But the last proper test topic for test 4 is going to be these surface area problems that I'm about to demonstrate. Okay. So then, now on Thursday night, again, I will go ahead and go into section D on here, which is dealing with surface intervals and flux. So I can show you that. If you want to commit to doing that, I'll put one of those homework problems as a bonus on the test, okay? As a 10-point bonus to help you get a letter grade higher. And then that'll be 10 points that's just added with your test total. So you can say that's 10 points that adds to any test you want to. All right? So, surface. Yes, sir? Yep.
Oh, I said thank you for that.
Oh, you're welcome. Okay. All right, well, what do you see the bonus first? Don't thank me yet.
Yeah.
So, surface area for parametric surfaces is calculated by ultimately doing a cross product magnitude, starting with your parametric surface. If you're given the parametrization for a surface, and it's written in this vector form, like I've done for the last couple of examples, and keep in mind, this is still the same thing as, x equals this equation, y equals this one, and z equals this one. But because of the way these surface area integrals pop up, it's best to represent them as a vector equation. And the way you set up the surface area, well, actually, this is your first version of a surface integral. So in actually calculating this, I'm really introducing you to a surface integral. The double integrals we've seen so far, we've always done double integrals where the domain was the xy plane in xy coordinates, or the xy plane in r theta coordinates. So your double integrals up to this point, the domain has been some region D in the xy plane. This is new, okay? This is actually using a surface out in space as the domain of a double integral. So instead of you integrating over, maybe a rectangle in the xy plane or inside a circle in the xy plane, you're integrating over maybe that yarmulke we just grabbed here a second ago. Your domain of the double integral. Now notice, that's in 3 space, but it's still a 2-dimensional domain because the highest geometric attribute you can measure for a surface is surface area. You can't measure volume for a 2-dimensional surface, even though it's in 3-dimensional space, you see? Think about our yarmulke. How thick is our yarmulke? Not a real yarmulke, but the one we grabbed here. Infinitesimally small, yeah. It's only 1 point thick because it's a set of points on this sphere that are cut inside this cone. So it has no thickness, but we still have to represent it in 3 space because it's that surface as that part of the sphere. So it's a 3D representation of an object that only has a 2-dimensional geometric measure. You see, the only thing I can measure on the surface of a sphere is surface area.
Does that mean we have no volume in the 4th dimension?
No. Well, yeah, I guess if you analog it to 4 dimensions, you could say that the surface of a 4th-dimensional object is a 3-dimensional volume. So, the perimeter of a 2-dimensional object is a 1-dimensional circumference. You see, so it's always sort of 1 dimension off like that. You have to represent the sphere in 3D because it's a surface, but how thick is it? It has no thickness because it's just the points on the sphere. It's not the inside of the sphere. It's just what's on it. So since it's only, really just a 2-dimensional surface, you can only measure its 2-dimensional area. So instead of your domain being a part of the xy plane, and apparently this is now sign language for the xy plane because I've been doing this like crazy, but if you're only integrating over the xy plane, you have a 2-dimensional domain. But that's not the only 2-dimensional domains you can use for double integrals. You can use the surface of some other function as your integration domain. Now, that's hard to picture because, at least when I introduce double integrals, I can say the domain's here in the xy plane, the function's up here on top, we're measuring the volume that goes from the xy plane up to the surface, and that's a 3-dimensional quantity, okay? In this case, it's kind of hard to imagine the surface of that sphere being your domain, and then what kind of volume are you actually measuring? I mean, the best thing to think about is maybe your integral measures something that requires knowing that surface area. Maybe like some kind of, I'll go back to the whole Coulomb example, maybe net coulombs per square unit on the surface of the sphere, and then your double integral sums up the net Coulomb contribution on that surface. I'm on the outside looking in on physics, but just for instance. So instead of integrating over a region of the xy plane, you're integrating over a surface. And just like when you integrate a triple integral over the region V in 3 space for the function 1, it gives you volume. If you do the double integral to the number 1, it's always going to give you an area. If you do a double integral of 1 for an xy plane region, it tells you the area of that region of the xy plane. If you do a double integral for the function 1 over a surface, it's going to give you the surface area of that region in space. Now, so this is the theoretical definition of a surface area integral. You'll never actually use this. When you put pencil to paper to actually calculate a surface integral, that's what you got to do. You take your parametric surface, and notice it involves some partial derivatives. You haven't done partial derivatives with vector functions because up to this point, your vector functions were only functions of t. So you talk about r prime, regular Calc 1 derivative, because your only variable is t. But now we can talk about r being a function of u and v, and it having a component-wise partial derivative with respect to u, and a component-wise partial derivative with respect to v. When you cross-product those two together, and you take the magnitude, if you think back to the first geometric application of cross-product magnitude you recall.
Normal too?
Well, normal does create a normal vector. So the cross-product itself produces a normal vector to r partial u and r partial v. But did you ever see the geometric application of taking the magnitude of your cross-product for a pair of vectors?
That's the other
It would compare with a problem like this. If you have a vector, say u, and a vector v, and imagine them being drawn tail to tail, like this, have you ever had to calculate the area of that parallelogram? So that was introduced to you. Oh, okay, well, I need to do that. If you want to calculate the area of a parallelogram that two vectors span, you see, this calculation gives you a vector that's perpendicular. So if I did, well, in this case, just so that it's actually coming out of the board, if I do v cross u, see the right-hand rule there would be v to u. So v cross u would be a vector pointing this way. But if you take that thing's magnitude, the length of the cross-product vector is the same value as the area of the parallelogram that they both span. You actually just had an aha moment. So that's kind of a cool fact for a handful of you. So since I'm calculating surface area and the cross-product magnitude gives you those parallelogram areas, what you have to imagine is taking this surface in space and breaking it up into little bitty patches. So that way you have a little, r partial u going this way and r partial v going this way on these particular patches. So for one part of the surface, let me draw an exaggerated picture of it. So here's our surface out in space. We're trying to get the surface area up. So if we're at this corner point right here, r partial u is possibly maybe that tangent vector heading off in that direction, and r partial v is maybe a tangent vector heading off in this direction. Because partial derivatives still measure, tangents. And so if I calculate the magnitude of their cross product, it approximates that particular patch of the area on the surface underneath it, you see. And then if you allow the partitions on the surface to shrink smaller and smaller, then these patches get smaller. They actually get closer to being the proper surface area itself, almost like little patches on a quilt. Like a little, this is a big square patch on this quilt. And then if I allow these patches to get smaller and smaller, then those patches approximate the surface area a lot more accurately for the smaller size of the patch that I'm actually using. So as these shrink infinitesimally small, down to infinitesimally small points on the surface, then these cross product magnitudes actually sum up all the way across the 2D, the surface itself, to add up to the total surface area contribution. So you're summing up in the u and the v dimension every single quilt patch. Pretty cool picture, because most of you have seen a quilt. Every single quilt patch that these sort of shrink down to get a total value of the actual proper surface area of the surface itself. Okay. I think I lied on this first problem. If it works the same way it did this past fall, I actually allude to needing your table of integrals here, because I think when I first typed this up, I anticipated this turning into a messy integral. But I don't think it does, if you set it up correct. So in order for you to calculate the surface area, this is described as the surface of a cone. We've done u cosine v with x and u sine v with y before. Remember, that much gives you that disk in the xy plane. But if your z component is squared, it gives you a paraboloid. But if your z component is linear, it goes up, with linear cross sections like a cone. So this is a part of the cone. 0 to 1 for u means this would be a circle that begins with 0 radius out to 1 in the xy plane. And then if u goes in the z direction as well, it pitches up to a height of z equals 1, 2. So it's just that snippet of the cone. And from 0 to pi, though, for v, instead of 0 to 2 pi. So it's just the first and second quadrant portion of it. Yeah, so it's half of a circle. So it ends up looking something like this. This would be the top of it. And here's the bottom of it coming down to the origin. So it looks something like this. Positive x, positive y, with z coming up through the middle like that. So we're really just finding that surface area right there. Just that half cone, because you're stopping. Now, you didn't have to graph this. I mean, in order to do a surface area, you're going to be given the actual parametric representation of the surface, and you'll have to be given the limits of your variables that are your parameters, the u's and the v's. All you need to do is to construct this guy right here. That is the nuts and bolts of doing surface area. But it is a construct. You have to go through the actual building of the integrand because it requires doing two partial derivatives. It requires doing their cross product, and then requires doing its magnitude. So it's a pretty intense, I won't say intense in terms of scary. It's just got multiple steps before you can get to the integration. And the good news is, those are your interval limits. The region D that you're integrating over is representing some region of the UV plane. So all your parametric surfaces will be given to you as well as the actual limits, so you don't have to imagine something being projected down to the XY plane. Those are your interval limits in whatever order is most convenient. DU, DV order or DV, DU order. Let's see what this turns into first to see which order we want to actually commit to. So, two things I need. I need R's partial with respect to U. I also need R's partial with respect to V to begin the construction of the cross product, the magnitude inside there. So remember, the cross product itself is not a scalar. The cross product is a vector, and then you want to take the magnitude of that vector. So there's really 4 steps before you finally get to what your integrand looks like. So R's partial with respect to U, just make a sweep across. The I component, V is a constant and U is my variable, so this partial with respect to U should be 1 cosine V. True? The J component partial with U behaves the same way, 1 sine V. And my K component depends only on U, so U goes to 1 there in doing its partial derivative. So your partial derivatives for a vector function, just like for regular functions, just keep in mind who's the variable, who's the constant, and treat them accordingly, using the correct derivative rule that you need, or treating it as a coefficient. Then start with a fresh copy of your surface up here, and now do its partial with respect to V. So U is a constant, cosine V needs to be differentiated. So this would be negative U sine V, right? Then the derivative for my J component with respect to V, U is a coefficient, sine V becomes cosine V. And then my K component, again, only depends on U, so its partial with V should annihilate it. Okay. How long has it been since you did a cross product? Oh, a couple of days for you. So yeah, so some of you more recent than others. For some of you who are only doing it in this class, it may have been, maybe since February or something. So now I need to do R's partial U cross with R's partial V. Now, in all honesty, I mean, there is a specific order to doing cross products, but since you're ultimately taking the magnitude of that cross product versus V cross U, it's the same thing. So it doesn't matter if you flip your order up, because you're eventually going to apply the Pythagorean theorem to this vector. But the way I do my cross products,
do you bring the ones over?
I don't do it that way. I do. I mean, is that the way Beth taught it? Is to put the phantom columns over here?
No. She did the 1, 2, 3, and then
block
the columns. But I saw that on one of your videos.
So I usually just, if you neatly draw the two vectors that you're crossing here in one row each, so you can kind of describe the I column, the J column, the K column like this, I just sort of imagine this being my determinant. And the way I've evaluated them, and let me double check and see if this is consistent, because it has to be, it's the only other way I know of. She crosses out to get the I component, you cross out the I column and the top row, and then you do this times this minus this times this.
Cofactor expansion.
Cofactor expansion, yeah, with a +1 cofactor there, -1 +1. Okay, so those of you who don't know what that's about, you'll see it soon in matrix. But yeah, you're just expanding by cofactors. So 0 minus u cosine v is the I component of my cross product. So minus u cosine v. And then cross out the j column. And for those of you who don't know what the whole cofactor thing is, remember, what I do is usually a 2x2 determinant. You do this times this minus this times this. I tell my students to switch the order. Do this times this, negative u sine v, minus this times this, only for the j component.
You add them?
Pardon?
And you add them?
And you add them, yeah. It's still that minus that. You're just reversing the order of subtraction because of that -1 cofactor. Or did Beth just say take the opposite of the one you get here? If you remember. Okay. Because if you do a 2x2, it's usually this times this minus that times that. But that's the wrong order for this particular position. So if you do it that way,
So
0 minus negative, you get a positive u sine v. You need to change it to negative u sine v down here. And then my k component for the cross product, you're back to a normal 2x2. So right here, cosine v times u cosine v is u cosine squared v. So if you don't mind, well, I'm just going to write that down there. And then minus, this times this is minus negative, so it should become plus. Plus u sine squared v. So ultimately, what does that k component for the cross product become?
2u.
Be careful.
No.
Be careful.
No.
Factor the u out.
Just
u. It becomes u times 1. It's tempting to say that because you see a pair of u's there, but then when you factor it out, you've got cosine squared v plus sine squared v. So ultimately, it does just become u times 1. So your correct cross product, committing a new line to this one.
Can you zoom out a little bit?
Oh. Everything else is still the same. Negative u cosine v for I, negative u sine v for j. And then the k component, carefully, make sure you make that a u in this case. So we're almost done. We're 3/4 of the way there. We've got our cross product built. We just need to find its magnitude. And the magnitude of the cross product is your actual integrand. That's what you integrate. And so your integrand for one of these surface area double integrals should default to becoming a function involving u's and or v's. And remember, the limits on u and v here define your limits for the actual surface integrals themselves. So all I need to do now is just build that integrand, the magnitude of my cross product. Just apply that three-dimensional Pythagorean theorem, open up a big old radical, if you need that much, square each component, and notice the squaring is going to get rid of your negatives. U squared cosine squared v plus u squared sine squared v plus u squared. All right, Tim, can I put you on the spot? What does this one simplify to? In the radical.
Just u squared plus u squared?
So in this case, it does become 2u squared. You've got the u squared here that you can factor out because they produce that cosine squared plus sine squared identity. So you ultimately actually have u squared times 1 plus the spare u squared on the end. So in this case, you do actually get root 2u squared inside the radical. That's a mistake I've seen a handful of students make in the past, is they see this and they think 2u, and then when this pops up, they forget that you can factor the u squared out, and really it becomes 1 plus 1 inside there, so you actually get 2 there. So, I mean, and can I simplify this integrand?
U squared 2?
Yeah, you can pull a u out, and so you can actually make it easier to work with where it's just u squared of 2.
I didn't know.
So, in my opinion, surface areas for parametric surfaces is much, much sweeter than leaving them in terms of x, y, z coordinates. Because that's an easy integral. That is my integrand for the surface area calculation. Going back to the way surface area is defined, is once you've done the magnitude of your cross product of those partials, like these two, you do the double integral over the region D, where again, D is the underlying UV plane region. The UV region is defined right there. So that means, finally, after all those steps, the surface area of this snippet of the cone, we do the double integral of the function u squared root of 2, and that's easy order either way, unless you can do dv order. But again, once you commit to your order, that defines how you're going to use your limits. Up here at the statement of the problem, u ranges from 0 to 1. So if I'm doing u first, I want to put the 0 to 1 here. V ranges from 0 to pi, so V's limits will go with the outer integral. And the rest is test 3. You integrate that with respect to u. Well, we'll say du. So there's really 1/2 u squared times the square root of 2.
We just chose the order because of what we had left.
Yeah, and you could do dv du order. Either order is fine because you're integrating over constants with respect to u and v, and that I'm really just having to integrate u. Square root of 2 is a coefficient, so I could have pulled the square root of 2 to the very front, since it's just multiplied by the u. So when I plug in u equals 1, I get 1/2 square root of 2, and then minus 0 when I plug in 0. So after integrating u, I get square root of 2 over 2. And then when I take that and finish the rest of the integration, but again, there's no dependence on v now, so remember, the trick is 0 to pi, we just multiply that by pi. But since, just in case you've forgotten that, because you've slept since then, a handful of you, you integrate that constant to become root 2 over 2v with respect to v, and then you plug in your pi limit, and pi is the only non-zero contribution. And so that turns out to be your surface area. You missed it.
Oh, I got that actually.
Oh, you're a done deal. Okay. Cocky. In a good way. I'm bragging on you. So yeah, you got the same answer. You're still good as gold. I just have to take my time just to make sure I got all the steps down pat. And plus, this is being filmed for posterity. And so that represents that two-dimensional surface area of that half of the cone. The positive y-axis half is pictured right there. So if you needed the full lateral surface area, going all the way around, what would it be?
Identical 2 pi?
Yeah, it better be twice as much as this. It better be just pi times the square root of 2. Yeah. So now there is a formula for the surface area of a cone. I've just never committed it to memory because I know how to do this. I think it involves like the square root of a squared plus b squared or something like that, and then a 2 pi revolution. I just can't remember it because I've never needed to. But yeah, that should be the surface area. If you find that surface area formula, feel free to double check it. This is a cone that has a base, has a radius up here of 1, and has a height of 1 also, because the u value goes from 0 to 1. So you've got a 1 radius and a 1 height. So if you double check it with the height and the radius version of the surface area formula, and then cut it in half, and that should be it. That represents the last kind of problem you can see on test 4. So again, test 4's official material will cover 10 problems, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 problems, stopping with the surface area for parametric surfaces only. And then what we cover Thursday night, I'll introduce you to surface integral flux and show you a couple of problems on that, and then just describe that as a potential bonus. So something like that will be the bonus for test 4. Do you have any questions? Okay. Clear your throats. Have a good remainder of your Tuesday, and I'll see you Thursday night. Oh, keep in mind, test 3 or test retakes are available in the testing center up through Thursday. Not getting them done by Thursday, sorry, there's not going to be an extension. Tomorrow is the latest day you get, till 7:30. So if you have to, use tomorrow to your advantage. And I'll try to get those graded back to you on Thursday, or at least